Good afternoon, all of you. Good afternoon. Am I audible? Please do this.
Yes, sir, audible.
Okay, okay. Thank you. Let me now share the PPT. Hello. Am I audible? So yes, again, am I audible?
Yes, sir.
Yes,
Okay,
sir.
okay. ठीक है. So means if I am remember, yes, last time around, I think before a long break that we discuss about the unfolding where we talk about the unfolding application. Okay, so over there we have seen this application where you can actually think about performance optimization using unfolding. Retiming can be also used, but sometimes retiming cannot be applied where unfolding will give you the better performance. So the cases that is the DSP program cannot be implemented with the iteration period equal to iteration bound without the use of unfolding. So that is the first case. I think maybe I can start. Okay. I think somebody has started recording. Okay. So DSP program cannot be implemented with the iteration period equal to iteration bound without the use of the unfolding. So iteration bound is a maximum limit through to which you can reach. Okay. But through retiming, it would be impossible for you to reach to the limit of the iteration bound. So where unfolding would help you to actually reach to a limit, to a iteration bound where you can sample your algorithm. So unfolded DFG can have a sample period equal to iteration bound. Okay, so that is ultimately a thing. So we will see the case. So this example, if I remember that we have discussed last time where we have unfolded it two number of times. Okay, now what is the case over here? If I look at the critical part, then the critical part will be SQR, which is 411, which is 6. Okay, now if I look at this critical part and if I think about implementing a retiming, then at most I can get it up to 4 because this is the maximum value of this particular node S. Okay, with the retiming, you can get the maximum performance up to a one particular node delay. So here S and T both are having a delay of 4. So actually two critical part, SQR and TQR. But for a board, the node S and T having a delay of a node is 4. So you cannot go beyond 4. So maximum that you can go up to 4. But if you look at the iteration bound, then iteration bound is 4 plus 1 plus 1, this loop divided by 2. So that is 3. Okay. So iteration bound says that the minimum value that you can achieve for this particular DFG is 3. But if I go with the retiming, then I can reach up to 4. I cannot reach up to 3. So if I want to do this, then I need to apply the unfolding. How many times I need to unfold? So that is 2. So that how you can decide it, that computational node time is u, tu greater than t infinity. Then tu by t infinity should be used. So see, t infinity is, what is t infinity? Iteration bound. Iteration bound is 6. And tu, that means maximum node delay. So here S and T is having a maximum node delay. So that is that is T capital U. So Tu and capital T infinity, that is 6. So 4 by 6. So that will give you 1.5. But this is actually a upper limit. Okay, so this shows that you need to go to a upper limit, that is ceiling function. So ceiling function says that 1.5 integer value is 2. So that means you need to unfold this 2 number of times. So this way, this particular graph has been unfolded by 2. That is the unfolding factor is 2 being considered. And with that you get the maximum performance. Another case is when the iteration bound is not an integer. So here if you observe this particular graph, left hand side, PRUV, 1 1 1 delay is there. Okay. So I am talking about original graph before unfolding. So over there PRUV. So these 4 nodes are there, each having a 1 unit delay. And for that, if I find out there is a 1 loop only there, so that is a loop bound equal to iteration bound. So there is only 1 loop. So that loop will contribute towards the iteration bound. So here if you observe that the iteration bound is 4 by 3. Now if you look at this particular graph, and here you observe that the critical part is, what is critical part? R2U, that is a delay free part. Over there the time unit delay is, or critical part delay is 2. So that means you can reach, you can get maximum get up to 2. Here the number of delay element is 3. So if you rearrange any delay element, then also there will be one particular part when there is a no delay element. Because there are 4 nodes and each node are connected with the edge, and you have a 3 delay element. So obviously you can put it at anywhere 3. Okay. So 1 will be the path which is a delay free, and where the 2 consecutive node will come into the in series, and where that the critical path delay would be 2. So through retiming also you can get up to 2. But what the iteration bound says that you can go up to 4.3. So that is 1.33. Okay. Now here the iteration bound is not integer. Since your always the delay of a particular node will be always an integer. So if you are having an iteration bound which is a non-integer, then non-integer iteration bound cannot be reached with the help of the retiming. So now if you want to do it, then ultimately you need to apply, or you need to think about having a unfolding. So you can unfold this particular graph. So this unfolding can be of 3 times. Okay, because how you can define it? 4 by 3 ultimately you need to make this as an integer. So iteration bound is 4 by 3. So if I multiply by 3, then I will get the iteration bound. So you need to find out lowest j. So that is the formula what is being given over here. I think it is there. Okay. J into T infinity greater or equal to Tu max. Okay. So 4 by 3 you need to find out j through which you can make it integer. So here it is 4 by 3. So you need to multiply with j. So that j minimum value is 3. Okay, it can be 6 also. 6 will give you the integer value to 3. Sorry, 4. But if you put a j is equal to 3, then 4 by 3 into j. So that is 4 by 3 into 3. You will get 4. So that is the iteration bound that you will get it. So here the unfolding factor 3 is being applied. Now we know that how we can unfold it. So you can apply this unfolding formula over here, and you will get 3 unfolded graph like this. I believe this you can do it. So 4 by 3 into 3, that is the idea. Now this both case can be combined. Okay, so we are considering two cases. The first case is when the particular node delay is greater than your iteration bound, then you need to apply unfolding where retiming fails. Another is when your iteration bound is not integer. So at that time also the unfolding will save you, where you will get the performance up to the iteration bound. Now this both case can be combined. So that can be considered as a third case. So when the longest node computational time is greater than T infinitive and T infinity is not integer. So this is my first case and this is my second case. If both case combined, then also I can use it unfolding to get the performance up to iteration bound. So minimum unfolding factor J can be find out J T infinity greater or equal to Tu max. So J is an unfolding factor. T infinity is 4 by 3. Tu max is 6 over here. So here I think there is no graph for that, but Tu max is considered as a 6. So for that the J is equal to the 6 is the value that you need to choose. So when the longest computational node Tu max is greater than T infinity and T infinity is no longer integer, then also you need to use a unfolding. Now we will talk about another application of the unfolding where you can apply. So parallel processing. Parallel processing is already we have discussed, where multiple input you can process at a time. Okay. So in a parallel processing, there are different category. First is a word level processing and another is a bit level processing. Now what I mean by word level processing? So word level processing is something where I have a J unfolding factor. So world serial architecture. So that is a architecture which actually perform the world level parallel processing, where J number of parallel processing loop creates the architecture while J word per process in a clock cycle. So I am talking about the word. Now word could be any integer value. Now it may be a case that I have a total 8-bit value, but my word size is 4. So that means 4-bit can be processed at a time. So that means I require 2 clock cycles. So 8-bit is my total value, but at a time I can process only 4-bit. So in one clock cycle 4-bit, another clock cycle 4-bit. So at that way 8-bit could be processed in a 2 clock cycle. Another is a bit level parallel processing. So bit level parallel processing is further divided into the 3 category. When bit serial processing, that means ki 1 bit is processed at a time through our architecture. So that is considered to be slowest one. Only 1 bit will be processed. So if you want to process 8-bit, then you require 8 clock cycle, because at a time only 1 bit could be processed. So for a 8-bit, the 8 clock cycle you require. Then bit parallel. So 1 word of W bits is processed at every clock cycle. So over here what happens that it is something like that number of bits could be processed. Okay. So maybe I have a 8-bit, but at a time only 2 bit can be processed. So that way, if I need to process 8-bit, then I need to run for a 4 clock cycle. Okay, so that we will see with the example. Then digit serial. So when n bit process per clock and a word is processed in a W by n clock. So that means 8-bit I need to process, but at a time W word is processed. So how many clock cycle I require? W by n. So maybe I have a 8-bit to process, but at a time 4-bit can be processed. So 8 by 4. That means 2 clock cycle I require. So in order to understand this, just try to understand this bit parallel. That means if 1 bit, second bit. So here total 6 bit can be processed parallelly. Okay. So in a bit parallel architecture, when I say that, then only a single bit input is applied. Another is a digit parallel or word parallel. This is digit serial. Okay. Where you can have a multi-bit. You can process parallel. Here in a bit parallel, only single bit can be processed parallel. Okay. So if I want to process 8 bit, then only 1 bit will be processed. So that way I need to apply 8 bit at a time. Similarly, if I want to go for a same thing with the digit serial, so over here you can have a multiple bit at a time you can provide. Okay, so that way you can process it. 1 minute. Okay, so basically in a bit parallel architecture, 1 bit at a time apply, so that way multiple bit you can apply. But over here, if I want to process 8 bit, then 8 bit at a time you can apply. Okay, in a digit serial you want to process 8 bit, but 8 bit cannot be applied parallelly. You can apply either 4 bit or 2 bit. So that means not all the bit you can apply parallel. In a bit parallel architecture, all the bit you can apply. Whatever the bit you need to process, all the bit you can apply parallel. But in a digit serial, whatever the number of bits that need to be processed, that cannot be applied parallel. But there is lesser number of parallelism is available. So that is also possible. But over there, the number of clock cycle is larger. Here, the hardware point of view it is larger, because if you consider that whatever the process you need to complete it for a single bit, that you need to replicate 6 number of time, because 6 bit A0 to A5 is being processed parallel. Okay, in a digit serial architecture you require such 2 kind of parallel processing unit. Okay, so here the hardware requirement is somewhat larger, but in a bit parallel it is a largest one, while the efficient hardware design is a bit serial architecture. In a bit serial architecture, only 1 bit at a time will be processed. So if you want to process 8 bit, then you require 8 clock cycle. But the advantage is only single hardware unit is there that is taking care of all the bit processing. Okay, so bit serial architecture is the most efficient in terms of the area wise, but speed wise it is slowest one. Bit parallel architecture is require larger number of hardware, but in a 1 clock cycle it can complete the process. Digit serial architecture is in between solution. Okay, so where number of clock cycle is not single, it is not also the number of bits, but it is in between solution. Okay, so here I can process 3 bit at a time. Okay, so ultimately total 6 bit is being processed in a bunch of 3 tree, and that way it requires total 3 clock cycle, because you have a 2 parallel such unit. Okay, so 3 input you need to apply at the first instant. In the second instant you need to apply 3 bit input, so that way the 6 bit input will be applied over here. Now how you can do it? Okay, so word level parallel processing, it is simple concept of unfolding. Okay, so over here this is your FIR filter. Probably in a type of, at the time of the retiming you may be gone through this architecture. XN is there, here CBA, so here ultimately A will be multiplied with the XN, then B will be multiplied with the XN, and C will be multiplied here 2D, then you can add it and you can generate the YN. So this is one FIR filter. Now this is being converted into the DFB like this. just bottom one. On the left hand side, topmost block is a FIR filter, and just bottom to that is a DFG, which is actually a simple DFG where all the nodes, this CBA, capital CBA is a multiplier and D and E is a adder. Okay, so this particular DFG is equivalent to this particular FIR filter. Now this is being unfolded 3 number of times. So how you can apply the unfolding, that you know that there is a U, there is a V, so U to V. So that the node instance is U, I modulo J, and with the delay of I plus W divided by J, that is a floor function. So that is a delay. So that formula you know. So that you need to apply to each and every node. And this way you can get it your middle one graph, which is the 3 time unfolded graph. And then you are doing a reverse engineering. C, capital C is multiplier. So here for every capital C0, C1, C2, you are putting a multiplier. Similarly, B0, B1, B2 is a multiplier, which is being multiplied by B. So that's what. So from here to here, whatever you have done, that reverse way you are doing it. From capital 0, you are putting this. That is a multiplier with multiplicand value is C. Similarly, capital B0 is where the B is multiplied. Similarly, capital L is 0, where the A is being multiplied. Like this, you are doing. Okay. Now, another thing is bit serial architecture. So bit serial architecture, how you can do it? Bit serial architecture is the slowest one, where single bit is being processed. Okay. So if I want to go for a 4-bit adder, so this A plus B, here A plus B is there. So that is a 4-bit adder. A is 4-bit, B is 4-bit. So that's why W is basically defined as a 4-bit. So my sum will be of also 4-bit plus one extra bit that I need to consider is for a carry out. Okay. So when I consider this adder, this is the block level representation. So when I add A and B, then there are 2 outputs. One is a sum, another is a carry. So here there will be 2 output. So on a left hand side, you have an input A0, B0, and third input, which is actually being connected downward with 4L plus 0. That is my C in. So for a full adder, I have a 3 input, A, B, and C in. A is of 4-bit, B is of 4-bit, and C in is always a single bit. That C in is nothing but C out of my previous adder. Okay. So whenever I do A0, B0, then it will generate S0, and it will also generate the carry out. This carry out, then this D flip flop is there. The D flip flop is being connected to my C in. Now what is the role of this D flip flop? Yes. Why in this we have connected D flip flop?
Provide delay.
Provide delay. Oh, that's true. But why we need to provide delay? Can you elaborate it?
We have to add the carry in next bits.
Okay. So ultimately you need to ensure that whatever the carry is being generated, that carry should be applied to my next iteration. Okay. In present iteration, A0 and B0 will be added. It will generate sum 0 and it will generate carry out. But that carry out, you need to ensure that it would be considered when A1 and B1 will be added. Because A0, B0 will generate whatever the carry out. That carry out will be considered for a carry in for my A1 plus B1. So at that time, A1 plus B1 and this particular loop, whatever is coming out, that you need to consider. So that you need to ensure that it would be for next iteration. In order to ensure that it would be considered for a next iteration, I need to put a delay. So ultimately in a one iteration, it will take a 1 clock cycle. So in a next iteration, definitely next clock cycle is there. So in order to define that, the D is being considered over here. So this D is being considered. That will ensure that this particular carry out will be considered as a carry in for my next iteration only. So this way A1 B1 will generate some S1, but whatever the carry out, that will be considered carry in when I will add A2 B2. Similarly, A2 B2 will generate some output S2, but that carry out will be considered when I will do the A3 B3. So like this it will be considered. So the idea is how to obtain the bit level parallel architecture, how we can apply the unfolding concept. Okay, so that we will see that for this particular way, for this particular architecture, how we can apply the bit level parallel processing architecture. Now bit level parallel processing architecture is possible by applying switch. Okay, now just observe it. Let's consider over here. देखो यहां पे अगर आप देखोगे तो कैरी इन के लिए so there is a switch. One part of the switch is 4L plus 0, another part of the switch is 4L plus 1, 2 and 3. Now what is the role of switch? Switch is probably in the network theory you have just gone through that there is a one switch through which at one particular instance you are making it at one position, at another particular instant you are putting it into the another position. So that way you are making a circuit. So the similar way over here, the function of the switch is to just toggle the switching according to the different instance. Now here the W is 4, that means I need to do the addition 4 number of times, because I will do addition of A0 B0, I will do the addition of A1 B1, I will do the addition of A2 B2 and I will do the addition of A3 B3. So these 4 instances are there. So for every 4 instances I need to define the position of the switch. Now when I start my addition A0 B0, that means my first instance is being added. At that time what is C in 0? What is C in? So there is no previously any addition is being carried out. So there is no previous C out. So ultimately when I start my addition, at that time I am considering C is equal to 0. So this C is equal to 0 is being considered by 4L plus 0. Now this 4 is defines how many times this loop will run. 4L, L stands for loop, and before that the number is written 4. So that 4 is defined that this loop will run 4 number of times. So that's why it is 4L. Okay, 4L. That means that this loop will run 4 number of times. So that integer 4 into L, you need to understand it. Now 4L plus 0. So that means first instance of that loop. Second instance of the loop will be defined 4L plus 1. Third instance will be 4L plus 2. Fourth instance will be 4L plus 3. So 4 instance of the loop will run 4 number of times. So there will be 4 instance. 4L plus 0, 4L plus 1, 4L plus 2, 4L plus 3. So 4L plus 0 is my first instance. So whenever I am starting an addition, when I do A0 plus B0, at that time the switch will be in this position. That is my initial instant, or that is my consider for first instant, 4L plus 0. So A0 plus B0, 4L plus 0 will be there. So that is being connected with the ground. So here Cin will be 0. So this connection is being connected with the ground. This 0 stands for ground. So Cin is 0. So A0 plus B0, 0. That will generate some 0 and that will generate some carry out. That carry out will now go into the room. At that time 4L plus 1 will be initiated. So that will be available. Yes. 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 Any issue? Somebody is asking. Yes. Any doubt? Okay. So A0 plus B0 will be added. It will be added to a 4L plus 0 instance. It will generate S0 summation and carry out. So carry out will be considered as a carry in. Then I need to consider my second instance, which is 4L plus 1. So A1 plus B1 plus there is a third bit which is 4L plus 1 that is being added and that will generate S1. At the same time, the carry out will be generated that is equivalent to 4L plus 2 instance. Similarly, A2 plus B2 will be added that will generate S2 and that is 4L plus 3 instance. That 4L plus 3 instance will be added with the A3 plus B3 that will generate S3 and whatever the carry out is your final bit that you need to consider as a carry out. So this way this particular bit serial architecture work. Now how to draw it, that we need to understand. So when I consider a bit level parallel architecture, at that time I need to process W word or with J unfolding architecture. So let's consider that I have 8 bit to process, but I have unfolded 4 number of times. That means 4 bit I can apply only at a time. So in order to process 8 bit, I need to run for a multiple clock cycle. Over here it is 8 by 4. That means 2 clock cycle I need to run. So 2 clock cycle I require in order to provide my all 8 bit input. So that is being applied. So W is equal to W dash J. So that W dash J we need to find it out. W is already known, whatever the number of bit that you need to process. J is an unfolding factor that is given to you, or maybe you can decide as per your resources, and that way you need to find out W dash. So that W dash you need to always find out, that is nothing but W by J. Okay. So this will be governed by this equation, that is a two-step process. WL plus U. U is the instance, L stands for loop and W stands for number of times this loop run. Okay. So WL plus U will be mapped to J in bracket W dash L U by J plus U modulo J. This U is known to you. J is known to you. Instance, you know that instance has to be given to you. Okay. That J is given to you. W is given to you. But from that you need to find out W dash. So that is your first task, that you need to identify W dash. You will be more clear where we will see with the example. Now here, how the mapping on an unfolded graph will be done. U percentage J will be mapped to V U percentage J with the switching instance of this W dash L plus U by J. Okay. So let's try to understand with the example. So let's consider that there is a one particular simple graph which is given like this: U2V 12L plus 1 7 9 11. So that means 12 times this loop will run and the instants are being defined: 12L plus 1, 12L plus 7, 12L plus 9 and 12L plus 11. Now J is equal to 3, W is equal to 12. Okay, so this is given to you. J value is given and W number of bit that you need to process, that is also given. Now W dash you need to find out. What is the equation of W dash? W is equal to W dash J. So what is the W dash? W is equal to W dash J. W is 12. J is 3. So W dash is 4. I hope you are getting. Okay. So just follow this equation. WL plus U instant, that will be mapped to this. So WL plus U, that is being mapped to this equation. So J is 12. W dash we have find out 4. L you need to put as it is. U by J. U is what? U is 1, 7, 9, 11. So these 4 are the value of U. So 12L plus 1. So for that U is 1 consider. So 3 is my J. In bracket this is W dash L. So this is 4 is W dash plus this is u. I am just following this equation only. J is 4, sorry, J is 3, W dash is 4, L you need to put as it is, plus U. U is instant, so here 12L plus 1, here it is 1. So this one is nothing but this one. Okay, divide by J, so J is 3. So 1 by 3 floor function plus U modulo J. So U is 1, J is 3. So that is being written. Such a simple equation is being written. 12L plus 1 is equal to 3 into bracket 4L plus in a floor function 1 by 3 plus U modulo J. So U is 1 and J is 3. So this way you will get 3 4L plus 0. How? 1 by 3 floor 0.33 floor integer is 0. So 4L plus 0. 1 modulo 3 output is 1. So this will be the output. Now what is my second instant? 12L plus 7. So 12L plus 7 I have considered. For that similar way you need to apply this equation. U is 7. So here only U will change. All the parameters remain as it is. Here there is a, see in this equation there are two U. U is coming two way. U is over here and U is over here. So 12L plus 7. So this U value you need to replace it two places. 7 and 7. And according to that whatever the value that you need to consider. 12L plus 9. So again U is 9. So here and as well as here. 11. Here it is 11. Here it is 11. Okay. So this way. And how they are mapping? They are mapping U modulo J to V modulo J. So this is a mapping of U to V. In simple unfolding, we have seen that U of I map to V of I modulo J. But here U of U modulo J will be mapped to V of V modulo J. So that is being identified. तो ये modulo J की वैल्यू है. ये यहाँ पे जो आ रहा है ना वो वैल्यू है तो वो यहाँ पे लिखिए. ठीक है, ये यहाँ पे. So this way you can define it. So just maybe you can try to do it. Bit level parallel processing. So there is another example. Okay, now here A to D, and then now if you look at this over here, this equation whenever you says that whenever you go to U to V, at that time there is no delay. So this switching instance is always applied to a edge where there is a no delay. Okay, mark my word, what I am saying, switching instance, this formula is applicable when there is a no delay in at my edge. Now here U to V, the example was simple because there is no delay for U to V edge. But now if you consider this A to C, now A to C there is a switching instance 6L plus 1, 6L plus 5, as well as there is a delay 2D. Okay, now here A to C is having a switching instance as well as delay. But what our normal formula says that U to V, whenever there is a switching instance, there is no delay. So that's why over here, what could be the case? Here, if we want to apply the formula, then we need to add one dummy node. So here D is being applied at this particular edge. You just observe A to C जो है ना, उसमें मैंने एक D node, dummy node introduce किया है. वो dummy node introduce करने का फायदा क्या था कि मेरा D to C only switching रहेगा और A to D I have a delay. A to C I have a delay as well as a switching. So that I have break it by inserting a dummy node which is D. Now for this D, A to D there is a delay and D to C there is a switching. So there is no way that dummy the delay and switching all come together in a one edge. In a one edge A to D, there is a delay, and D to C, there is a switching instance. Okay, now you know that how you can apply unfolding to A to D. That is a simple example that we used to solve it before our midterm. D to C, when there is a switching instance, we need to apply this formula U to V. Okay, so that formula you need to apply. So 6L, J is 3, W is 6. So what is your W dash? J is 3, W is 6. So J, W is equal to W dash J. This formula just remember. So J is 3, W is 6. So W dash will be 2. So here you just observe that this W dash is 2, J is 3. Here there are switching instance U 0, 1, 2, 3, 4 are being applied, and you are just putting that value over here. So you are applying 0, 1, 2, 3, 4, 5, and this different U instance you are putting it over here, and this way you are getting this solution. So I believe that this you can try it out. So with this, the unfolding graph will look like this. Okay, now again, whenever you are drawing your final graph, this D is a dummy node. Dummy node is a temporary node. So that you need to remove. So that dummy node, you need to remove it. So here, you just observe that A is connected to D2, and that D2 is being connected to C2. So A0 is connected to D2, D2 is connected to C2, but this D2 is dummy node. So I will just simply remove it. So A is connected to C2. A0 is directly connected to C2. Here, this is the last line. Okay. So that way you need to remove the dummy node in a final graph. And this way you can get the final graph output. So similar way, this is a 4-bit serial adder unfolding is being drawn. जो हमने एग्जांपल देखा, तो उस एग्जांपल में similar way switching we need to apply. So in a switching again A2X, B2X, X2X, X2D, X2D जो है वहां पे आपका डिले एलिमेंट है, और D2X में स्विचिंग है और Z2X में स्विचिंग है, पर वहां पे डिले एलिमेंट नहीं है. सो आई थिंक दिस इज अ सिंपलर वन. देयर इज नो नीड टू हैव अ डमी नोड. यू कैन अप्लाई for A2X, B2X, X2S, X2D, the normal way unfolding, and from D2X and Z2X where there is a switching is applied, you can apply this way the formula, whatever we have talk about. So just try to go through it, and this way you can complete this example. So I just leave it up to you that you can complete this example by yourself. Maybe you can go through a book. In a KK Parikh, a similar example is given. You can try it out. If you are having any issue, maybe you can ask me in a next week. Okay. So next week, actually, maybe we can start the offline classes from the next week. The only thing is to jumping towards the online class for this week, because just to take a precautionary action, because actually means in our department there are few cases that is being reported for a COVID-19. Okay, so that's why just to ensure that anyhow today there was a lab where I cannot reschedule it. So at that time I have taken a chance and I have conducted the lab. But for a classes, maybe for a at least for a VLSI DSP for a 1 week, maybe we can have this offline classes. Okay. So at that time, I will just go through through PPT. But if you have any doubt personally, then you can contact me next week where we can discuss it. Okay. So actually, I don't have any fear from you, but you need to take care from my side, because I was in close contact with the Vijay sir, and who is getting the infected recently. Okay. So that's why I am just trying to avoid it, and I am just considering myself as a somewhat isolated from different people. So that's why I have just conducted this week, because at least 1 week I need to be separate out from the student. So that's why I have conducted my class for online. So if everything goes well, then maybe from next week onwards, we will start with the offline class for VLSI SPA, and that we will go in probably in VLTC only. Okay. Yes, any doubt you have, then let me know. I would be more than happy to answer.
Sir, I have a doubt in that first mapping graph, sir, U to V, when we are mapping, sir, U0 to V0, and the second mapping, sir, I have some doubt in that, sir.
Okay.
Yes, sir.
So
Yes,
over
sir.
here,
Yes.
over
Yes.
here.
Yes,
Okay.
sir.
Okay. What is the exact doubt?
How is this mapping is happening here, sir? U1 to
Okay.
V1.
See, this equation you should first remember. WL plus
Yes.
U. J W dash L plus U by J. U modulo J. So in this equation, first of all, W is given to you in every problem.
Yes, sir.
J is given to you. W dash you need to calculate. How you can calculate W is equal to W dash J. So here in this problem, J is 3, W is 12. So you can easily find out W dash is 4. Is it clear?
Yes, sir.
Okay.
Yes, sir.
Now U is unknown here. See, J is there, W is there. With J and W, you can find out W dash. Now this U is an instance. Now in the original graph, this instance is given. This you just observed it 12L plus 1. So U is 1. 12L plus 7. So U is 7. 12L plus 9. U is 9. 12L plus 11. U is 11. Okay.
Yes, sir.
So that different U value you need to put it. This U is 1. So this U1 is put it over here. Sorry, over here and over here. So in this particular formula only I have put U. And that way you will get the this particular loop structure. So that I
Yes,
have
sir.
done from 12L plus 7, 12L plus 9, 12L plus 11. And this way you will get this 4. And that you need to put it like this. Now, how the mapping of the node is U to V. So ultimately U of this formula, U of U modulo J will be mapped to U of modulo J. See, U over here is 1. So 1 modulo J, J is 3. So 1 modulo 3 and V modulo 3. So the over there you just observe 4L plus 0 instance is there. So ये U1 और V1 के बीच में ये है. So that is directly comes out from the formula. Okay. The only thing is
Yes,
probably
sir.
I am not showing it in the board, so probably it will be very difficult to visualize it. But I ensure you that if you do it on paper by yourself, then you will get it. And if you are not getting this, then you can ask me next week. There is no problem.
Yes.
Okay.
Yes. Thank you.
Okay.
Yes, sir. Thank you.
Okay. Any further doubt? Okay. If there is no further doubt, then we can end up our session. And as I announced that probably this week onward, this week, I would just like to conduct my classes online, and that is actually advisable also because most of the faculty are doing that only. So okay, so see you next time. I think tomorrow I have a lecture, so we will do the same way. Okay, thank you.